Howdy! Here we are with the Logs and Exponentials chapter 15. This is lesson number 2, Exponentials and E. Now to start with, exponentials are something that we've come across already, way back in chapter 3 when we were looking at functions. So what is an exponential function? Well, an exponential function looks like this. F of x equals a to the power of x. So your index is x, and a is just going to be a different number. A cannot be 1 though, because then you would just have 1 to the power of something, and 1 to the power of anything would always just give you 1. And also, a is always going to be bigger than 0. So this is what we looked at way back in chapter 3, exponential functions, and really the graph of them. So we were looking at the graph of f of x equals a to the power of x when x was bigger than 1. And we found that an exponential graph always passes through a couple of points. Matthew, hit us with one of the points. What is that? Good, an exponential, if you remember, always passes through 0, 1. Matthew, why does it always pass through 0, 1? Yeah, because if x was 0, well, we'd have some number to the power of 0. Anything to the power of 0 is always going to be 1. So it always passes through 0, 1. What's something else, Connor, that it passes through? Yeah, good, it always passes through 1a. Because if we have a to the power of 1, well, that's just going to give us a. So 1a is another one it will pass through. Graphing an exponential, what does that look like? Yeah, you're going to graph it and then there's going to be a gradual increase, and the increase is going to increase each time. So, graphing it, it will look something like this. You've probably heard of things increasing exponentially, and if something increases exponentially, it's going to increase quite quickly by larger amounts each time. So graphing it, you will get something that looks like this. Again, passing through the point 0, 1 and then 1a. If a is bigger than 1, that is what you will get. So if a is bigger than 1, the graph will always be increasing, and it is therefore known as a growth function. However, say we mixed that up and a was not bigger than 1. Say a was between 0 and 1. What would that look like? Well, again, it would always pass through those 2 points, 0, 1 and 1a, but it wouldn't be increasing each time, it would be decreasing. So you would have something that looks like that. Again, you've still got those 2 points. So it wouldn't be a growth function, it wouldn't be increasing, it would be known as a decaying function. So, to sum up, what we've really looked at so far with exponentials, an exponential is when you have a to the power of x. A is not equal to 1, a is bigger than 0. If you graph it and a is bigger than 1, it's going to be increasing each time, and it's known as a growth function, and a decay function would be when it would be decreasing, and that would be when a was between 0 and 1. Let's move on then to the next part of exponentials. So in maths and in physics and in nature, there is a special base that often occurs, and that base is known as the base e. E is a special number in maths, just like pi. It's never ending, like 3.14159, it's just going to keep on going. E is another number. And to 3 significant figures, or to 2 decimal places, it's 3.72. You'll need your calculator for any of these E questions. There is an E button on the calculator. You will use that. Let's try it just now. Try e to the power of 1. Try that on the calculator. Give me it to a few decimal places. What do you get? Yeah, you should be getting e to the power of 1 will give you 2.718281828. It is not repeating right the way down. This is just a coincidence. It's just random numbers. But you get 2.718281828, and so on. Just keeps on going. It's a special number in maths. So y equals e to the power of x is the exponential function with base e. Sometimes you will see it written as exp, x. So exp for exponential, so the exponential base e. A little bit of history for you. The use of the letter e to represent the value 2.718 is attributed to Leonhard Euler, a Swiss mathematician born way back when Mr. Ross was a little boy in 1707. Euler was also responsible for the notation we use today, including pi, woo, and f of x. He is one of the most prolific and creative mathematicians of all time. Hey, hey. So, let's try some examples then with e. So example 1, evaluate each one of these to 4 significant figures. If we have e to the power of 4, Mazamo, you'll be loving this. What do you need? Calculator! Yes, you need your calculator for these. So, e to the power of 4, put in e, the index here is 4, so e to the power of 4, and what do you get? Good, 54.60 to 4 significant figures. Let's try another one, e to the power of 6.7, what do you get? 4 significant figures, try it with me. Good, 812.4. Let's try another one, e to the power of negative 2.8. Just fire that into the calculator. Boom, boom, boom. What do you get? Good, you get 0.06081 to 4 significant figures. Let's try another one, e to the power of 5m, where m equals 12.6. Chelsea, how would you do this one? Good, work out 5 times 12.6 first of all. That will give you 63. Work that out to 4 significant figures. E to the power of 63, you get 2.294. But you also get times 10 to the power of 27. You get a massive number for that one. Okay, huge number. Let's try another one. Example 2. This time we've got a worded problem. A lot of the time for these exponential problems, we will be given some story. And what we need to do is pick out the information and then try and solve it. But it will be worded problems that come up. Don't let them put you off, just read through it and pick out the information that you need. So here, the speed at which a rumour spreads in a school is exponential. Largs Academy, shout out to Mr. Marshall, has 900 pupils. If 2 of them start a rumour, then t days later, n students will have heard it, where n, the number of students in terms of t, is equal to 2e to the power of 1.36t. So part A, check that at the beginning, when t equals 0, only 2 students are involved. And B, taking Monday as t equals 1, how many students will have heard the rumour by Thursday? So first of all, well, we're told n in terms of t, the number of students, after so many days equals 2e to the power of 1.36 times t, times the number of days. So for part A, well, at the start we know t equals 0. So when t equals 0, we could work out n 0. We're replacing t with 0, which means on the right hand side, replace t with 0. So we'd have 2e to the power of 1.36 times 0. Obviously, if we work that out, well, anything times 0 is 0, so it becomes 2e to the power of 0. After that, anything to the power of 0 is 1. So we'd have 2 times 1, and obviously 2 times 1 is 7. I'm joking, it's 2. So you can get that answer. After that then, you can say that there are only 2 students that are involved at the beginning. Woo! Next one, part B. Taking Monday as t equals 1, how many students will have heard the rumour by Thursday? So this time, obviously, if Monday is 1, Tuesday will be 2, Wednesday will be 3, and Thursday will be 4. Yeah. So Thursday is going to be day 4, so we know t equals 4. So we're going to do the exact same thing again. Here we've got this function n in terms of t, so this time t is 4, so we replace t with 4, so it becomes 2e to the power of 1.36 times 4. Work that out, 1.36 times 4 will give you 5.44. Put that into the calculator, 2 times e to the power of 5.44, and that will give you 460.88. You could always write that down, 460.88 pupils, but because it's talking about different pupils, you tend not to get 0.88 of a person. Also, I wouldn't round up the way because it's not quite at 461, so I'd probably round that down to 460. Do not worry about anything like this though in an exam. They would not be as ambiguous as this. They would give you it, so they would tell you around so many significant figures or decimal places, or you would get some nice answer in the end. Okay, 460 is what I'd go for. If you went for 461, that's fine. 460.88, that's fine as well. Let's try another one. Example 3, due to inflation, prices increase annually. The price P of items after t years is given by P, in terms of t, equals P0 or P0, e to the power of 0.05t, where P0 is the original price. So part A, if a pint of milk, glug glug glug, costs 88 pence, how much will it cost in 3 years' time? And part B, if a rail fare, choo choo, is £20 now, how much will it be in 15 years' time? So let's go with part A. Well, we're told that the price of items after so many years. So PT, the price after T years, is given by P0, where that's the original price, times e to the power of 0.05t. So I've got this here. After that, the price after 3 years is what I'm wanting. So replace T with 3. So P0 is 88. The time is 3 years. So I'd have P after 3 years equals 88. That is what P0 is. That's the original price. Times e to the power of 0.05 times 3. From there, 0.05 times 3 is 0.15. Work that out on the calculator. 88 times e to the power of 0.15, and you get 102.24. Remember though, P0 was in pence, so really we're working our answer out in pence, so it's 102.24 pence. Obviously, we don't get 0.24 pence, so if you write that down in terms of pounds, that would be £1 and 2 pence, or 102 pence would be absolutely fine. A pint of milk will cost £1, 2 pence in 3 years' time. Let's try part B. If a rail fare is £20 just now, how much will that be in 15 years' time? So we're told the original price. We're told P0, that's £20. And we're also told the time, it's 15 years' time. So we're going to replace T with 15. So we'd have P 15 equals P0 is the original price, so that will be 20, times by e to the power of 0.05 times t, but t is 15. So we get that. From there, if you work out 0.05 times 15, that gives you 0.75. So it's 20 times e to the power of 0.75. And from there, if you work that out, you get 42.34 to a couple of decimal places. Therefore, the rail fare is £20 just now, but in 15 years' time, it will be £42 and 34 pence. Woo! Example 4. Atmospheric pressure changes with altitude according to the formula AH equals 1.03 e to the power of negative 0.0001 h, where AH is the pressure in kilograms per square centimetre at 8 h meters above sea level. So part A, what is the pressure at sea level? And part B, Mount Everest is 8,848 metres high. Calculate the atmospheric pressure at the top. Correct to 3 significant figures. So first of all, well, we're told AH, the atmospheric pressure at such a height, is given by 1.03 times e to the power of 0.0001 times h, where h is the metres above sea level. So we know if we want the pressure at sea level, well, at sea level, the height above sea level is 0. Okay, we're not above it, we're at sea level. So the height is going to be 0. So really, we're wanting a 0. Replace h with 0, so we get a 0. That's 1.03 e to the power of negative 0.0001 times 0. Work out the index. If you multiply this by 0, well, you just get 0. E to the power of 0 is just going to be 1, so it's 1.03 times 1, which gives us 1.03. So we know then that at sea level, the pressure is just going to be 1.03, and the units are just given here, kilograms per square centimetre. Part B. Mount Everest is 8,848 metres high. Woo! Calculate the atmospheric pressure at the top. Correct to 3 significant figures. So for this one, well, it tells us the height. So we know the height is 8,884. So really what we're wanting to do is we're wanting to take this and we're replacing h with this number. So we'd have a 8,884 equals 1.03 e to the power of negative 0.0001 times the 8,884. From there, if you multiply these numbers together, it will give you e to the power of negative 0.8848. Work that out on the calculator and you get 0.42518. Really, we're asked for it though to 3 significant figures. So to 3 significant figures, that will be 0.425. And you can just finish that off with a sentence saying at the top of Mount Everest, the pressure is 0.425 kilograms per square centimetre. So that's it for exponentials and looking at E. I'll give these questions a shot. Let me know how you get on. Best of luck. Bye.